is called heat transfer. Now, heat can transfer by three methods. One, conduction. Two, convection. Three, radiation. Convection, I don't need to teach you, there's no calculation, but please read it through by yourself. And also, the last part I'm not going to do with you is called global warming. Also, no calculation, read through by yourself. Okay? You should come out if the last question 15 in the objective, global warming, okay? But go through it, okay? So, it's actually quite important thing to know in this world. That's what caused all the uncertain weather, okay, in all over the world, okay. So now, so what is the difference between these three methods? Now let me give you an example. Now, if you take a beaker and you heat it, you got water. You don't stir the water, it will take a long time for the temperature here to be the same as the temperature here. Okay. Because in the beginning, if the water is not boiling, it's going to take a very long time, because the only way the heat can travel from bottom to top is by conduction. That means the molecular collision between the water molecules. Okay, that's going to take some time. Of course, when the water boils, is a different method. So if you take a stir and stir, then you are causing convection. Okay, so convection will move the thing, and then the heat will travel faster. Okay, without moving the molecule, water molecule, the only way the heat can travel is by conduction. For example, in a room, now even if you switch on the aircon, you find that the room will cool down slower. By switch on the fan, it will cool down faster. Why? Because the fan is moving the air. So you switch on the fan, you're increasing the transfer heat by convection. Okay, if not, the convection rate will be very slow. Okay, because the only way heat can travel is by conduction. Okay, I mean, if you don't switch on the fan, the convection rate will be very slow. Where the heat will mostly travel by conduction. Conduction is the flow of heat mainly by molecular collision. Okay, so these two, you have calculation. This one, read it yourself, okay? Radiation is the one that you get the heat from the sun. Okay, the sun heat comes to you by radiation. Okay, so now today, let's start with this. This is the one that comes up quite often in the exam, which is good because it's easy. Now, so first of all, we are going to study how heat travel by conduction. Okay. For example, in the solid, we are not talking of metal for the solid. How the thing travel? So for example, solid, you find that the molecule vibrate about their main position. Okay. I'm not going to draw a lot. Okay, so let's say when you heat a particular part of a solid, so at first you find that they will vibrate like that. Okay. But when you heat a particular section, you find that the ion there, or the atom there will gain kinetic energy. So what happens? They vibrate with bigger amplitude. And then when they vibrate with bigger amplitude, they collide with the neighbor. So once they collide with neighbor, they transfer energy of neighbor. So the neighbor also will get an increase in kinetic energy. So they will vibrate with bigger amplitude. And this will continue. So they will knock the other neighbor. And then by means of molecular collision, you find that the heat travel from one section to another section of a solid. Okay. So this one, make sure now to explain, that's quite important. Now, so this is mainly in solid for not metal. For example, solid like wood, stone, okay, any other solid that has got no free electron. But for metal, now metal are usually very good heat conductor. Why? Because metal, the heat transfer this way, but the heat also transfer another way. Because metal got a lot of free electron, and the free electron move very fast in the space between the ion. So when this, so what happens is this. Now, if you hit a particular area, you find that the electron cloud will go through. So when the electron cloud come here, you find the electron will gain energy and they'll move faster. So when they move among the ion, they'll collide with other electrons, and also they collide with the ion. So in the process, they transfer energy. So because they move very fast, you find that the heat energy will be transferred very fast. That's why metal gets hot very fast. Understand? Understand not? Now, okay? So the difference between metal and other solid is that metal got free electron. That's why metal can conduct heat very fast. Okay. This is a very important thing. Now, this topic got only one formula. Okay, so not like thermodynamics or so many formulas. So now, okay, now we are going to see the formula. Okay. Now, we are going to define a quantity called thermal conductivity. First of all, we need to understand temperature gradient. Now, temperature gradient is actually the change in temperature per unit length. Okay. So, the unit we use is Kelvin, because basically this one is the same as this and this. So, SI unit is Kelvin meter. So, Kelvin per meter. Okay. So temperature gradient is Kelvin per meter. Let's consider a thick bar, which is properly lac. Lac means insulated against heat. Okay. So let's say it's lac. Lagging. Lagging means insulator. So let's consider two sections. Huh? Now I will follow your note. Okay. Let's consider section M and N. Let's say temperature theta I, theta F, and this X. Right? So let's say heat is traveling this direction. Heat also represented by letter Q. Okay. So temperature gradient. Usually, I usually write like that, but now, so by definition, temperature gradient is the change in temperature per unit length. So it will be change in temperature be like that per unit length. Okay. But if we use like that, actually, according to definition, temperature gradient will be negative because this one is higher than this. So this quantity will come out negative. But in calculation, try to avoid this. In calculation, we won't use this. In calculation, we'll reverse the thing. We'll use this. So that we get positive. Okay. So we are going to use the magnitude of the temperature gradient. Okay. Don't use negative. If negative, we sure get. You sure will feel negative. Okay. So now, so we are going to use this. Okay. Now, so let's see the formula. Now I do an experiment. Rate of heat flow is dq over dt. Let's say the cross-sectional area is A. Okay. You find that the thicker the bar, the faster the flow. Right? So it is direct proportional to the cross-sectional area. So the thicker the bar, the faster it conducts heat. Number two, you find that the bigger the magnitude, the bigger temperature gradient, the magnitude of temperature gradient, the faster the flow. Okay? I'm going to use this. In the end, I would do like that, okay? Faster, okay? So combine these two, you will get this equation. I write like that, same time. Okay, so you want to form an equation, you add a K. So total will be like that. Now this is the only equation you need to know for this section. K is called thermal conductivity. And here we define thermal conductivity using the equation. We define it this way. Term 2, you are going to see quite a number of quantity defined using equation. So you better learn it. So if A is 1, this one is 1, then K is dq over dt. So this is how to define. Thermal conductivity is the rate of heat flow per unit cross-sectional area per unit temperature gradient. Okay. So thermal conductivity is the rate of heat flow per unit cross-sectional area per unit temperature gradient. Okay. Understand? So that is how you define. You define like that, you get full mark. Yeah. What?
Why the area will affect the rate of heat flow?
you got bigger area, the heat got more area to flow through. Okay. Anyway, they won't ask you this. It's common sense. You put a thin wire, for example, you put a thin wire and you put a fat bar like that. Let's say you put some ice here, and then put some ice here, and then put let's say 100 degrees Celsius, 100 degrees Celsius. Now you think lah, which one will melt first? This one will melt first lah. Not possible lah. Okay.
Okay.
And then sometimes common sense counts. Understand or not? In fact, common sense is quite important in physics sometimes. So of course, the fatter the area, the more heat can flow. Okay. If the thinner the area, cross-section area, then the heat cannot flow. You can easily show this by experiment. Anyway. They won't ask you why one.
Sir, I have a question. If we define the standard equation for the heat flow, the rate of heat flow, so we have to add on the negative sign or no need?
In calculation, don't use the negative sign, just use the magnitude of the temperature gradient, understand? You use a negative sign, after when we do question, you see why I don't use the negative sign, okay? There's no need. If they want the temperature gradient, then you can calculate and put a negative value, but when you use the equation, you don't use the negative value, understand or not? Does that answer your question?
Yes.
Okay. Well, you use negative value, you will get confused because this is a very easy topic. So just take a negative sign away, okay? If they want temperature gradient, yes, then you show the negative value, okay? Now, after when I do the question, you'll see. Now, this thermal conductivity is a measure of the ability of the material to conduct heat by conduction. It doesn't include convection or radiation. So if the thermal conductivity of material is high, that means the material will conduct heat by conduction very efficiently. Okay, so you can see the table there. See? Copper 380, air 0.03, okay? And then water, okay? Water 0.5. So that because copper is a very good conductor of heat by conduction. Air is very weak by conduction, but once you add convection, it's a different matter. Okay, so that's it. In the beginning, like the question asked just now, it was about confusion on how to use it. So let us, this first checkpoint is a simple one to teach you when to use negative sign, when not to use negative sign. Okay. So the only time you use negative sign, they ask you to find the temperature gradient. Okay. So now you have a bar, length 20 centimeter, cross-sectional area. You better change it to meter. The rod is perfectly lagged. It has to be perfectly lagged. If it's not perfectly lagged, there's only one other way to calculate. But now we don't talk about that yet. Okay? So you know what perfectly lagged? When perfectly lagged, the rate of heat flow is constant. That means the rate of heat flow here has the same value as here. Okay? Same value. Then we can use the equation. Now, it's maintained 100 and 0. Thermal conductivity is 3840. Now, find the temperature gradient along the rod. If I ask you find the temperature gradient, then you find the negative sign, like change of it, 0 minus 100 over 0.2. I get negative 500. Okay. This is the only time you need to use negative. Now find the temperature. This is 3 meters from the hot end. So no. 3 meters. What is the temperature? Now you don't need to use negative, okay? Just take this one and take higher minus lower over 3 centimeters. Okay, that's all. Don't use negative. You put in negative, then you got to reverse this as well. So 85. Okay, understand? Okay. Just take higher minus lower, then you don't need to use the negative sign. Okay? We have conduction through the rod. Okay? Also, no need negative, huh? Just put 500. And it's 95 joule per second or 95 watts. If you use negative, then it'll be negative 95 watt. Okay. Determine the amount of heat that flows through the rod in 50 seconds. This is the amount of heat in 1 second. In 50 seconds, you will take the time and multiply this. Okay, so 50 times 95. Okay. So I want you to go through the checkpoint. Be to get used to the formula only, okay? You can do it now, no need to copy the answer because we are going to finish this. I give answer for your reference only. Do it now, no need to copy the answer. Now finish these two and then finish 3, 4. We'll do 1, 2, 3, 4, and then we go on to the next one. The next one we will tackle the question that might come out in the exam. Mm. Finish 1 and 2. Raise your hand. Mm, mm. Just get used to formula first before we apply further. You want to use centimeter also can, but be careful that you're consistent with your unit, okay? A lead copper a length of 100 centimeter, cross-section area 2 centimeters square, thermal equilibrium, the ends 100 and 0. Calculate temperature gradient along the bar. So again, temperature gradient will be negative. Okay, according to definition, but I wouldn't mind if there's no negative sign, but according to definition, there has to be a negative, okay? I don't think they'll mark you wrong, you don't have a negative sign, okay? But now I stick to the rule. Temperature at 20 centimeter from the hot end. So just take this and take higher temperature minus lower, and you get this. We have heat conduction. Just take your K, A, and multiply by 100. Right? Now, so now you know how to use. It'll be easy. So area 1 centimeter square. Length is 20 in a steady state. The two ends are 120 and 0. Thermal conductivity given, find the temperature gradient. Again, if you want to find a temperature gradient, you put negative on it. Power transfer. Now, 8 centimeter from the hotter end. So take this, take higher temperature minus lower over. Okay, very easy to use. Now finish 3, 4, then we go on to the next part. If no time, never mind, we stop here. Next week, we'll still finish all the theory. Looking at the time, I think we will finish at this checkpoint first. But I hope all of you are revising now. Please, you don't revise, it'll be too late. Okay. Now this one is just adding another simple formula. An oven with glass window. Okay. The window is 0.5 centimeter thick and temperature of the oven is maintained at 200 degrees Celsius. The outside is 21. Now temperature outside oven is 21. Find the amount of heat through the window in 1 hour. So 1 hour, 3,600 seconds. So you are given K. So put dq per dt. Now area is 0.3 times 0.2. Okay. So dq per dt will be Ka 200 minus 21 over d. Now notice, but this per second, so the heat required will be like that, okay? Take this and multiply by 3,600. Now, okay. And number 4, horizontal rod. Area 5 centimeter square is placed with one end in steam. Steam understood 100 degrees Celsius. And the other end at ice. I at 0, so 0 exactly, and no need to change in temperature, it will melt straight, okay? Thermal conductivity of copper is given. Latency of fusion. Now find the mass of ice melted in 10 minutes. So again, of course, you assume it's perfectly like, okay, we're not perfect like, you cannot calculate. Now, so just find, again, dq per dt equal to K, A, higher temperature minus lower, over L. So heat flow in 1 hour will be this. And the ice melt will be ML because it's already 0, so no need to find a change in temperature. So you know this, you know this, you know this, you find this. Okay. Now we'll do one simple part. I won't introduce the other formula yet. We'll just do something very simple. Comparing lead and unlead bar. We won't touch on the second formula yet, okay? Exam coming out will be based on next week, the second formula. So now let's discuss about bar that is totally not lead, that means not insulated, and the perfectly insulated bar. Okay, so let us see. So let's say this bar no lagging, 100 degrees Celsius, 0. Unlagged. Now we'll see how the temperature change. Let's say the line is L, doesn't matter. The value actually, the line is, whether a line is more important. Oh. And the other one is lag bar. That means when I say lag is perfectly lag, no halfway lag, okay? So this is totally lag, Now if you were to draw the temperature against distance graph, you get it to be like that. Whereas if you draw for this, you'll find that it will be like that. Okay. Now the reason is that the graph is like that is because there's heat loss. Now find that the temperature gradient, you're going to get a temperature gradient against, of course, if you draw temperature gradient, by definition, it must follow the negative side, okay? So find that this temperature gradient, the temperature gradient is actually the gradient of this graph, where you find that the theta per dl at 100 is greater than the theta per dl at 0 degrees Celsius. This is because there's heat loss. Let me put this as a, let's say M1, and this M2, then your M1 will be here, and your M2 possibly will be somewhere here. Okay. Then the heat loss, this is the only thing we can calculate for unlagged bar. So when you calculate heat loss, then you got to calculate the rate of heat flow here at 100 minus the rate of heat flow here at 0. That means the rate of heat loss will be this. So it'll be like that. You have to take this K, A, M1. Take this gradient minus K, A, M2. So this is the only calculation for unlagged bar. You find the real heat, the temperature gradient here. So the real heat flow at the hot end minus the real heat flow at the cold end, that will give you the rate of heat loss. This one, there's no problem at all. Because this one, the temperature gradient is a constant. Why? Because the rate of heat flow is a constant. Okay? So draw temperature gradient graph. You will probably get, you'll get like that, okay? That's all. No problem at all. So there's a difference between lag and unlagged bar. Because here, the rate of heat flow is just Ka, d theta per dl, which is a constant. Okay. So temperature gradient is actually the gradient of the temperature against length or distance graph. Okay. So today I think we'll stop here. Next